This video is going to discuss Fibonacci numbers and the derivation of phi. You've looked at some of the other videos that show the spiral arrangements and the petals on flowers. So now we're going to talk about some of the math, some of the Fibonacci numbers themselves. The Fibonacci numbers, the first one is a 1, the next one is a 1. Then to get to the third number, you add the two previous. So 1 plus 1 is 2. To get to the fourth number, you add the 1 and the 2 to get 3. Then add 2 and 3 to get 5, 3 and 5 to get 8, 5 and 8 to get 13, and so on. So we have what's called a recursive formula. The recursive formula has two seeds. F1 is 1, the first Fibonacci is 1, and the second Fibonacci number is 1. Then the formula is to get the next Fibonacci number in line, you add the previous Fibonacci number to the one before that. Now sometimes the subscripts confuse people, so let's look at some of those. F sub 6. Well, the little 6 just says to pick the 6th Fibonacci number in the line. So 1, 2, 3, 4, 5, 6. F sub 6 is 8. Let's try another one. F sub 12 divided by 4. Well, this whole fraction is in the subscript, so first we have to simplify that. F sub 12 divided by 4 would be the same thing as F sub 3. Well, that's the third Fibonacci number in the line. 1, 2, 3. F sub 3 is 2. Now for the next problem that we're going to do, we're going to need a few more Fibonacci numbers. 21, 34, 55, 89, and 144. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I wanted to get out to F sub 12 because the next problem I want to do is F sub 12 all divided by 4. Now I want you to notice the difference between these two problems. F sub subscript 12 divided by 4 is F sub 3. But this problem says do F sub 12 and then divide that answer by 4. Well, F sub 12 is 144. Then we need to divide that number by 4. And I think the answer is 36. So now I've listed the Fibonacci numbers. I've listed an n to the side here. N is just the order number, 1, 2, 3, 4, and so on. F sub 1 is 1, F sub 2 is 1, F sub 3 is 2, F sub 4 is 3, F sub 5 is 5, that's the only one that matches, F sub 6 is 8, and so on. We're kind of interested in the ratio of these Fibonacci numbers. So when I talk about the ratio, I'm going to take the next Fibonacci number in line and divide it by the previous one. So it's basically the bigger number divided by the smaller. So on this row I have 1 divided by 1. The next row is going to say 2 divided by 1. So this Fibonacci number divided by the one before it. So that's a 2. The next row has 3 divided by 2. And so on. Okay? I'm going to switch over to Excel so we can look at what happens when we do this. I've got a chart and it's going to plot the first ratio is a 1, The second ratio is a 2, and the third ratio is 1.5. So it started low, went higher, then went down a little bit. When I add the next one, 1.667, it goes up a little bit. Then it goes down a little bit. Then it goes up a little bit. And notice that it's just going to go up and down and up and down. But notice that the change is not quite as great at each step. It's going to go up some here, but not as high as the previous peak. Then it's going to go down, but not as low as the previous dip. And it's just going to continue to go up and down until pretty soon it looks like a straight line. Well, it's really not a straight line. It just looks like a straight line. If you were able to zoom in more, you would still see it going up and down and up and down. Now, if we look at this Excel, the numbers here, I'm going to fill this in farther. You can look out at in this case, the 5th decimal place. Here's a 5, then it goes down a little bit to a 2, then it goes up a little bit to a 3. And each of these numbers, again, is going up and down and up and down, but now you have to move out farther in your decimal expansion to see that up and down motion. Now, these little number signs here, that just means that there's not enough room to put that number in that spot because it's starting to get too big. But I'm going to continue to pull this down farther. And now you'll see that Excel is not seeing a difference in one number to the next and one ratio to the next. There is a difference farther out in the decimal expansion. If you could see more digits, you would see a difference between this digit, between this value and this value, but it would be pretty far out. What I want to look at today is when n, these numbers, get clear out to infinity, this number is going to actually equal phi. So let's start this back here, and we're going to derive that. So I'm going to do a little bit of fancy work with some fractions. The first ratio is just 1 over 1. The next ratio is 2 over 1. But I'm going to split that up in kind of an interesting way and write it as 1 plus 1 over 1. Now, obviously to you, 1 plus 1 over 1 is the same thing as 2 over 1. So the next one now is going to be 3 over 2. Well, 3 over 2 is the same as 1 plus 1 over 2. But I need to review a little bit about fractions with you. If you have, say, a number, 1, divided by another number, say 5/3, that's the same as, well, you know how to do fraction division. You invert the second number, so it's 1 times 3 over 5. So you invert the second number. Well, this is going to be the same as that. So if I look at the 2, this is the same as 1 plus 1 over, and the 2 is this, which is 1 plus 1 over 1. The next one, 5/3, that's a 1 plus 2/3, right? 3/3 plus 2/3, or 1 plus 2/3 is the same as 5/3. So using that little trick, it's going to be 1 plus 1 over 3/2. But 3/2 was equal to this. So that's 1 plus 1 over 1 plus 1 over 1. Are you starting to see the pattern? Do we need to really go through the whole thing? We will for one more. It's going to be 1 plus 3/5, which is the same as 1 plus 1 over 5/3. But 5/3 is equal to the material that came just previous. It's equal to this is 5/3. 1 plus 1 over plus 1 over 1 plus 1 over 1. So you're starting to get the idea. The next one, I would just add another 1 plus 1 over to the whole thing. So out at infinity, if I took one of the Fibonacci numbers and divided it by the one before that, as n gets really close to infinity, this is going to equal phi. And that is equal to 1 plus 1 over 1 plus 1 over plus 1 over. Well, I don't want to keep going because this is going to take a long time to write out to infinity. So I'm going to put some ellipses there that's going to show that that continues on forever. So if I just take this one layer, the outside layer off, do you notice that what is left, since it goes on forever, is still equal to phi? So what I have is 1 plus 1 over phi. And there's the equation we need to solve. Now you'll recall from your algebra class that in order to solve this, we have to multiply by the common denominator to clear that fraction. We don't want to have the variable in the fraction. So we have phi squared is equal to phi plus 1. Now this is an important equation to remember, so get that in your notes somewhere. Now to solve this, we need to move phi and the 1 to the other side of the equation to get a 0. And this is another important equation to remember. This will not factor, so if you remember solving quadratic equations with factoring, that's great, except for it won't work on this problem. So we have to use the quadratic formula. So phi is going to equal negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Now a is the number in front of phi squared. Well, that's a 1. There's a 1 in front there. So I put a 1 right there and right there. And c is negative 1. And b is the number in front of the phi. So that's a negative 1. There's a negative 1 in front of that phi. So this is going to simplify that phi is equal to 1 plus or minus the square root of 5 over 2. Now, most of the time we're going to be talking about phi equaling to the positive version 1 plus square root of 5 over 2. If you type this in your calculator, you'll get that phi is close to 1.618. So this is the exact answer, and this is the approximate answer.